No, okay, let's talk about something fun before we talk about the end term. So, this idea of building, this is just a fun exercise. So, I'll show you one of my expeditions last 2 years back in one of the Stanford buildings, and talk about how Stanford is implementing BIPV, right? So BIPV is this idea that you integrate this photovoltaics while you're making the construction of your building. So it's much more cheaper because a lot of your cost is your balance of system cost, and a lot of that is installation cost, right? So when you're actually putting the roof and you integrate photovoltaics into it, it's a much cheaper solution, right? So especially where there's a lot of construction happening, it makes a lot of sense to just make it BIPV. And there's some study that it improves the resale value of your house or your building as well, right? So
what's the lifetime of the module?
Well, you would like to use 30-year module, you will, yeah, but yeah, unless you're using some thin film or organic, usually the crystalline at least has 25 years at least. Okay, so to look about all the buildings at Stanford which are, including this BIPV, you can go to this website, and all the newer construction, at least the Huang Center, Night Management Center, Li Ka-shing building, they all integrate BIPV in their buildings. The crowning jewel of BIPV in Stanford is the Y2E2 building. So how many people have been to Y2E2? It has received a lot of awards, for being the greenest building. How many have been? All of you have been. Okay, awesome. So, let me ask you a few things. Let me see how many people observed all the BIPV or all the energy efficient features in the building. Okay. So, if you look on the roof of the building, it has 3 of these solar panels on each side, and for some reason you can't see it in this figure, but on this picture, but they are all 3 different technologies. So one is crystalline silicon, one is polycrystalline silicon, and the other one is a thin film. I'm not sure, but my opinion is it's CAD-10. So for some reason they decided to do an experiment and see which one works better over the lifetime. And there's a TV over a screen over there which shows each of them. So if it's a hot day, actually the CAD-10 one performs better. If it's a colder day, if it's more diffuse sunlight, also this one performs better. But if it's a normal day, then crystalline silicon of course has higher efficiency. So you can go there and actually see it on any particular day. If you go on that site, they also publish how they are performing. Yeah.
Since they're all more or less the same area, is the energy output of CAD-10 lower than?
Yes, it is. Yeah.
They show that as well?
No, I'm actually not sure. Okay, but this is a good place to compare. At least they're doing this experiment of comparing 3 different technologies. Okay. Now, so who actually works there? Let me ask you. You work there? Okay. So if you notice the windows on these Y2E2 building, they're different on different side of the building. So the north-facing side, it has a much lighter color of window, it's actually transparent window. But the south-facing part of the building, it has darker windows because prevent the building from heating up. And so this is on the south side, you have these much darker windows. And another feature which is, I find it very, very interesting, on the south side you have this thing called as a light shelf. So outside the window, you have essentially this kind of a shelf, you see over here, right? In the middle of the window, you have this shelf placed over here. Okay. So the purpose of this, does anybody know why do you do this? Okay.
To reflect light in natural light, you light up more than the natural light.
Okay.
Otherwise, the form would be more or less, the light would be focused very close to the window.
Okay. So sorry? So the purpose, at least what they've stated, is that there might be somebody who's sitting right next to this window. Okay, so for him, this light which is incoming is kind of disrupting, right? It's good in a way, but too much of it is bad. It heats up that place, and he has to switch on the AC, or he has to put the shades on, right? Either of those things he will do. So for this person who is sitting right next to it, you want to minimize the light which is falling on him. So the reason why they use this is essentially, and this is an arguable concept. One might argue that this is the best way or not, but the reason at least they have specified is that for him you want to minimize this direct light, but at the same time you want to make use of this light somewhere. So what you do is you put this shade in between, and it reflects this light into the building still, because this top of this thing is actually a mirror, and it reflects. If you go there and try to note, next time you go there, look at the building more closely. So the top of it is a mirror, and it tries to reflect the light back into the building, deeper into the building, where it creates it serves a better use here, as opposed to falling on the person who's sitting right next to the window. Okay. Let's see. On the south side of the building, if you go, you'll find this kind of a design for the basement, where especially on the south side where you have more light incident, people try to design this kind of a half basement where you dig a trench in slightly and make big windows over here. So the people, especially people who have grad students who have offices inside the basement, they get some light in, and seeing from your projects, it might have been better to just put a aluminum reflector here, but they have used this grass over here. But this is another way to enhance energy efficiency, or get the light in, especially to make this trench on the south side of the building. Okay. Now, the best feature that at least I find the most compelling or the most unique feature of this building is the design of the atrium. And it's designed, actually there's this pretty cool engineering which has gone into it. So if you look at the incoming light, right, it essentially, if you look at the conference room which are located inside the atrium, they are located in this card-off deck, or in this staircase fashion, where the conference room which is on the 4th floor, it's basically extending more into the atrium, versus the conference room which is on the 2nd floor, it's essentially encroaching. Sorry, it's in this staircase fashion. Right. So the conference room which is below is extending more, and the idea is that if you place them over here, each of these conference rooms will get some amount of light directly from the sun, right? And then they have optimized the design such that it works well if you're at the summer, or whether you're in the winter. They have put some reflectors over here, so if you go over there and notice the next time, the atrium is actually quite lifted up, and it's designed in this fashion where it has a triangular kind of a roof, and on the other side of it you have so this is the part which is which is facing up, and over here you have these reflectors, or you have these mirrors over here, so they can reflect this light, especially during the winter months. Okay. So next time you go there, look at it a little more carefully. I'll show you some more pictures. So this is the atrium. As I was showing you, the bottom conference room, it extends more, so that each of these conference room gets some amount of natural sunlight. One of the problems with does anybody know one of the main problems? What's one of the main safety hazards with atriums? Atriums are considered to be a big safety hazard. If you guys didn't know. Yeah, so if there's a fire in one of the floors, if there's an atrium in your building, it can spread very quickly to the whole building. So this is some feature that you'll have to go there, stand at the atrium and observe very carefully, because otherwise it's difficult to miss it. But if you look very carefully, beneath each of these atriums is this shed or this cover which automatically comes up when there's a fire. So whenever there's a fire alarm, these atriums automatically close down because you want to prevent the fire from one floor to going to the other floor. So you can actually see that shutter which is below, but you'll have to look very carefully. Okay. Another thing which is over here is that at the top of, so this atrium, the roof of the atrium is lifted up, right? So it's triangular shape and it's lifted up. And on the side of this lift are essentially these computer-constrained louvers which essentially let the hot air escape out. So one of the things that happens in this atrium is that light comes in, it heats up, or when the building heats up, the hot air inside the building rises, and you want to let that hot air escape out, and you want to detect the temperature. If the building is getting hot, you want to let the hot air escape from the top of the building. So Y2E2 atrium, it has these, again, if you go there, look at it more carefully now. Pranav, did you notice this?
I thought those were reflectors. I didn't know those were tools.
So there are reflectors as well, and then the reflectors on this taller side, so it's over here. But below there are these louvers over here, which control, which are basically controlled depending upon what temperature it is. And if it's getting hot outside, you open them so the air can escape out. Okay. There's some other features as well. For example, in terms of chilling, it uses direct water chilling. It's called active chilling. On the offices, they have these polygal material windows, so they give you privacy, but they still let the light in. And this is a very neat concept that if you use the restroom over here, whether you pee or you poop, you should press it in different directions because the water consumption is minimized according to that. Okay, so that's why if you do all that, you get what is called LEED Platinum rating. LEED stand for leadership in energy and environmental design, and the best rating that they give is platinum rating. So it has that LEED Platinum rating. I think a few other buildings in Stanford have it as well. The Night Management Center has it, I think. But yes. Okay. So I got the reason why I know all this, that when they initially opened, they were giving these tours where you could come in and they would show all these features. Right now you can't see this shutters of the atrium closing, etc. But they say at the time when it was opened, it was said that the energy payback time would be 4 years. So they have to, of course, invest a lot to do all this. On the Stanford side, they actually have a report of this. How well is it performing as compared to what they expected. But again, I'm not sure whether that's true or not.
And if by energy payback, you mean the amount of energy they spend building the building versus what's it saving over there?
Yeah, so it's the energy payback time. Remember we talked about
making the panel
both the energy payback and the money in terms of monetary cost payback. That whether the extra investment that they made, how many years would they recover it in terms of?
Is it 40 or?
So this building, one of the reasons why probably it's not performing as well is that they have quite a lot of active machinery inside the building. So a lot of the power consumption. So the panels that I showed you, actually I was looking at, I was hoping that they'll produce a large part of the power, but they only produce around 2% of the need of the building. So it's not very impressive, right? But in terms of all these features they have designed to cool it and keep it cool. I'm sure there's a grad student whose PhD is on figuring out how energy efficient it is, but again I don't have the numbers of that. It was supposed to be at least that's the number I remember when they gave us the tour, around 56% less energy consumption. I'm not sure whether they met it or not. Okay. So let's just talk 5-6 minutes doing a recap and talking about the exam. So it's on Friday, same time over here. We'll post some practice problems tomorrow, but the format is going to be more or less similar to what you're used to in your problem set. What I would recommend doing in preparation for this exam is to go over all the material. There's a lot of material we have covered, and it's kind of a large breadth class. That's what I started with. That it's going to be covering a lot of materials, and a good way to go back is to try to look at it again and just revisit it again now that you have some more understanding of it. And what I would consider a success is that hopefully if you can see commonalities, see connections forming in your mind between these different kind of cells, between things which are common between things. Or so if you start seeing forming those connections, then you have achieved the purpose of this course. Okay. We can look back what we covered. So we started with things like LCOE, energy payback time. Energy payback time was covered mostly in the videos. Then we talked about how crappy of a sun we have. Actually, we didn't know at that time, but now we know that the nature of the sunlight and how it limits the efficiency of my cell. So we talked about Shockley coils are limit, and then all this other stuff. And right, so we figured out, I'm just repeating the slide I had presented when I started the course, that we would cover all this, and I'm showing that what we have covered again in respect to what we had planned to. So we figured out we could use this mirrors for concentrating the cell, but you can't use too much of that because your efficiency rises as you increase your concentration, but it falls again because your cell starts to heat up, you have I square R drops and so on, right? And then we talked about these different limits of light trapping. We talked about different limits of thermodynamic limits of both light trapping and efficiency of the cell. So it's a good idea to revisit them. Remember, we talked about Carnot efficiency limit, black body limit, Landsberg limit. What are those different limits? And now you have actually some ideas of, okay, how do I go about achieving those limits, right? So things like thermophotovoltaics, all the ideas we talked about today, which can help you achieve those limits. Okay, so revisit those. Then we talked quite a lot about these different kind of cells, and now you exactly know about all the different features on these cells, right? So why do we use texturing? Why do people use this all back contact design? What are some of the highest efficiency cells, the HIT cell, the sun power cell, right? We covered those in the video and also in the class, right? And then we talked about the manufacturing of crystalline PV, all the different processes, what limits their efficiency, surface recombination, Auger recombination. So revisit those things. Then multi-junction cells, and we had a good, a very informative guest lecture on multi-junction cells as well. Then during the process part of the stuff, we discovered that a lot of the cost is embedded inside the starting substrate material, right? And we had two guest speakers, one from Select Cell, one from Alta Devices. Both talk about these cells which try to minimize the cost associated, or try to use kerfless semiconductor to minimize that cost. Okay, so revisit all those things. Then more recently we have been talking about thin film technologies, and we have covered all four of them: amorphous silicon, CAD-TIL, SIGs, and organic photovoltaics. Each of them has some distinguishing features, but then they have some common features, such as all of them use these TCO materials, all of them use all of them try to use a flexible substrate, all of them try to have large surface to volume ratio, all of them tend to have better requirements in terms of light trapping. So these are some commonalities, but then there are some very interesting physics as well, so that organic cells which operate with this very interesting mechanism, right? So revisit all those things. The micro converters we didn't cover much, but we had a good guest lecture on this topic, and we understood why we need micro inverters and why it makes sense, especially for this residential kind of applications. Okay, and then last week we were talking about this thermophotovoltaics, and now we understand how does it compare with respect to normal photovoltaics. So the best efficiency we can get is around 20% for that disk, or around 16-17% for that for this tower kind of a configuration. And you have made a promise that next time when you go to Vegas, you will go and visit make a pit stop and visit this tower on your way there. Okay. So this is something that we have covered, and then the last two classes that I've been trying to emphasize are these, what is called as, at least the investors like to call them as black swan technologies, that we talked about all these concepts which, if they happen, like intermediate cell or impact ionization based cells, they are not demonstrated yet. People are researching on it, but if they happen, that would enable this third generation of photovoltaics, which is much more efficient and helps you to beat the Shockley corner limit. Okay, so that is a quick recap. I do want you to go back, revisit all the material. We will post some of the problems, practice problems tomorrow. On Wednesday, Shaheen will come and talk about, he's a different hat on things. He talks about more it from a from an investment point of view, what makes sense and what people are currently looking to invest at. So he'll give that a VC kind of a style talk on solar investment. That would happen on Wednesday, and the exam is on Friday. Okay, all right.